Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to my class. Now we are covering topics of module 3 and till now we have covered the wavefront, Huygens principle and its applications, then we talked about superposition principle and then we learned about the polarization of light, wherein we talked about linear polarization and circular polarization. Today we will start elliptical polarization. Just to remind you, a wave consists of E field and B field, and E and B field are perpendicular to each other, and these fields are also perpendicular to the direction of the propagation, which is usually designated by wave vector k. The k wave vector is a vector quantity and it has amplitude and certain say some direction, say z cap. Z cap is unit vector along z axis, and we know that this mod of k vector k is 2 pi by lambda. Okay, if it is in the vacuum, then it is designated at 2 pi by lambda naught, otherwise it is designated as 2 pi by lambda. Now the tip of electric field associated with the electromagnetic wave decides polarization. Now since E, the magnitude of electric field vector, is very large as compared to that of magnetic field, therefore polarization is always associated with the electric field. Okay. Now if electric field vibrates in a plane defined by E and k vector, which is shown here in this figure by these arrows, these are the amplitudes, the time variation of the E vector, then this type of electromagnetic wave is called linearly polarized or plane polarized. Okay. I repeat, if the electric field vector oscillates only in one plane, or in other words, if the oscillation of the electric field is confined in a single plane, then such a wave is called plane polarized wave or linearly polarized wave. Now apart from this type of wave, there is a second kind of polarization which is called circular polarization, and in case of circularly polarized light, the E vector, the tip of E vector forms a circle. Okay, in this case the E vector rotates like this. Okay. Now if you see from this direction, if we keep our eyes here and see from here, then we will see that there is a circle on the tip of the electric field vector rotates on this circle, and in this particular case the rotation is in clockwise direction. Okay. Such a wave is called right circularly polarized wave, RCP. If the rotation of electric field vector is in anti-clockwise direction, then such a wave is called left circularly polarized wave. Okay, like this. Okay, these are the two types of polarization we have studied till now. Now, in case of linearly polarized light, the magnitude of electric field vector is a function of time, it changes with time, while in case of circularly polarized light, the magnitude is constant, it is not varying with time or space, because it is the radius of the circle which it draws. Then what is changing in such kind of polarization? It is the direction of the electric field. Okay. Since the direction of the electric field depends upon the time, therefore, whole E field is again a function of time, and since E field is a function of time, it will generate B field and satisfies all the criterias of being of electromagnetic wave, of being an electromagnetic wave. Okay. Now, we will move further. Now, we will talk about elliptical polarized light, or we will talk about elliptical polarization. Okay. In elliptically polarized light, the electric field tip, it will generate an ellipse, and this is already suggested by the name itself. Yeah, and since it is ellipse, both the direction of the E field and the magnitude of the E field change with the propagation or change with time. Okay. Both direction and magnitude will not remain fixed. Okay. And linear and circular light may be considered to be the special cases of elliptical polarized light. We will discuss this sentence in greater detail in coming slide. Now, this means that the resultant electric field vector E will rotate and change its magnitude as well. Okay. In case of circularly polarized light, only the direction is changing, direction of the electric field vector is changing and magnitude remains constant, while in an elliptically polarized light, both direction and magnitude will change. Okay. And in case of elliptically polarized light, the end point of E will trace out an ellipse. Okay. And where would this ellipse be traced? It would be traced in a fixed space perpendicular to wave vector k. Okay. And we have seen that when a circularly polarized light propagate in space, it traces a spiral. Okay. And when we see it from the front, when we point our eyes towards the source, then we see that there is a circle, the locus of the electric field vector is a circle. Now, in the case of elliptically polarized light, when we will see towards the source, then the locus of the electric field, the tip of electric field vector will trace an ellipse. Okay. Now, depending upon some conditions, the orientation of the ellipse may change. What are those conditions? We will analyze right away. Now, let us again start with the two component of electric field, which are Ex and Ey. Okay. We also started with these two components when we were analyzing circularly polarized light. The same fields are also taken here. The only difference is that the magnitudes, the amplitudes of Ex and Ey in our case is different now. Okay. In case of circularly polarized light, E naught x was equal to E naught y, and that both were taken to be equal to E naught. Okay. But for elliptically polarized light, we will deliberately take these amplitudes different. Okay. Now, we will expand Ey. Okay. We will just consider equation number 38 and we will expand this cosine function. Okay. We see that cosine function is cos A plus B. We will expand this cosine A plus B and see what does we get. Okay. After expanding the cosine function, we get this expression a bit bigger. This is given by equation number 39. Okay. Let us also include the expression of Ex. How to include? we know that from equation number 37 E x is equal to E naught x cos k z minus omega t. Now, cos k z minus omega t in equation number 39, which is here, can be replaced by E x by E naught x. Okay. Let us do this. Let us replace cos k z minus omega t by E x by E naught x. Then this gives us equation number 40. Okay. This got a bit simplified. Let us again seek for the expression of sin k z minus omega t. What would be sin k z minus omega t? It would be equal to square root of 1 minus cos square k z minus omega t, and we know what is the expression of cosine k z minus omega t. It is E x by E naught x. Then after doing this, we get equation number 41. Therefore, we have now expression for sin k z minus omega t also. Okay, once we have this expression too, we will again substitute the expression of sin k z minus omega t back into equation number 40 here. Okay. Now, this is the final expression. Okay, we have substituted for sine function, we have substituted for cosine functions. Sine and cosine means sin k z minus omega t and cos k z minus omega t. After these two substitution, we got rid of k z minus omega t term. Okay. And this is the final expression which we got. Now, this is, and if we plot it, then we will get an ellipse. This is an expression of ellipse. Okay. And what is then this epsilon? We know that this epsilon was the initial phase or initial phase difference between the two electric field components, which were E x and E y. Yeah. This epsilon decides the ellipticity or orientation of the ellipse. How does it define? We rearrange the last equation, and this is the final equation of the ellipse, and this ellipse is making an angle alpha with E x and E y. Okay. What is the E x and E y? E x is pointing along x axis, E y is pointing along y axis. Okay. Now, the major axis of the ellipse, this drawing should be like this. The major axis of the ellipse is inclined by an angle alpha with respect to the horizontal, with respect to the E x axis. And how this alpha is given? Alpha is given by this expression. Okay. Using plane geometry, we can get this expression, and tan 2 alpha is equal to 2 E naught x into E naught y cosine of epsilon by E naught x square minus E naught y square. E naught x and E naught y are nothing but amplitudes of E x and E y fields, and cosine of alpha is here, where alpha is the initial phase difference between the two waves. Yeah. Therefore, using equation 43, we can generate an ellipse which is whose major axis is inclined at an angle alpha with the E x axis. Okay. This equation can further be simplified with some assumption. Then let us assume that the principal axis of the ellipse is aligned with the coordinate axis. What does it mean is that the major axis of the ellipse, we assume now that it is along horizontal direction, or it is along E x axis, or you can say that the ellipse is oriented in such a way that its major axis is along E x now, that is alpha is equal to 0. Okay. If we consider this, then equivalently we can write that initial phase epsilon is equal to plus minus pi, or plus minus 3 pi by 2, or plus minus 5 pi by 2. Okay. Saying alpha is equal to 0 is equivalent to saying epsilon has these values. Okay. Once we assume this, Then this complicated equation, equation number 43, which is an equation of ellipse oriented at certain angle, this gets reduced to a very typical equation of an ellipse, which we have already studied in our junior classes, okay, and this is now in recognizable format. Okay. Equation number 45 is the usual expression, okay, which is x square by some constant a square plus y square upon some constant b square is equal to 1, the typical expression of an ellipse. Okay, it is now in this format, okay, and we can easily now correlate them, we can easily recognize this expression as a ellipse. Yeah. Now, let us consider some special cases. Okay, what are the special cases? Now, we have given two electric field components. Out of these two electric field components, we derived or we did some mathematics and then concluded that this two field components will generate an elliptically polarized light. Okay. Now, this elliptical polarization, it may be a right elliptically polarized light or it may be a left elliptically polarized light. Both the electric field vector may rotate either in clockwise direction or in anti-clockwise direction. Okay, we have already devoted the last lecture what is the clockwise rotation and what is anti-clockwise rotation, how to know whether the electric field vector is rotating clockwise or anti-clockwise. We already learned this, okay, therefore, I will not repeat it here. What we know now is that given two electric field components and through these two components we derived an equation which says that the tip of the electric field vector will generate an ellipse and therefore, we name this type of this electromagnetic wave as elliptically polarized wave. Now, let us consider a few special cases. In equation number 45, we see that in the denominator we have E naught y and E naught x, which are the magnitudes, which are the amplitudes of the field components. Now, let us assume that E naught y is equal to E naught x and say they are equal to E naught. Then what will equation number 45 represent? In this particular case, equation number 45 will take this form E y square plus E x square is equal to E naught square. And what is this equation? This equation represents a circle. Okay. Therefore, we can safely say that in an elliptically polarized light, if the magnitude of the two electric field vectors are the same, then the ellipse will reduce down to a circle. Okay. Therefore, we can say that circularly polarized light is a special case of elliptically polarized light, and this justifies the claim which we made at the beginning of the lecture. Okay. Now, the second case, if epsilon is an odd or even multiple of pi, then what will happen? If epsilon is an odd or even multiple of pi, where is epsilon? The epsilon is sitting in equation number 43. Yeah? Now, under this condition what will happen? Let us see here. Now, if epsilon is an even multiple of pi, then cosine function, the cos epsilon would be equal to 1, sine function would be equal to 0, and therefore, we will have E x by E y is equal to E naught x by E naught y, which is a constant number. Therefore, we will have E x is equal to some constant and multiplied by E y. Okay, we will effectively get E x is equal to some constant and then E y, which is nothing but an equation of a line. Okay. Similarly, if epsilon is odd multiple of pi, then instead of getting this positive constant, we will get a negative constant. The orientation of the line will change. Okay. The line will rotate by some angle decided by the relative amplitudes of E naught x and E naught y. Okay. Therefore, if epsilon is odd or even multiple of pi, we have a straight line, and therefore, the resultant wave is a linearly polarized, okay, with opposite slopes, means the odd or even multiple of pi will generate plane polarized light with opposite slopes, okay, and therefore, it also justifies the claim that the linearly polarized light is an special case of elliptically polarized light, okay, and thus therefore, we saw that both circularly polarized light and linearly polarized light are special cases of elliptically polarized light. Okay. Now, let us keep varying the epsilon value and see what are the shapes which can be generated using a elliptically polarized light. Okay. And the expression of elliptically polarized light which we are using is this equation number 43. In this equation number 43, we will change epsilon and then we will trace out the equation and we will see what type of a structure, what type of curve we get. Okay. Now, in this figure, first we analyze the case where Ex leads Ey by 0 radian, then pi by 4 radian, then pi by 2 radian and so on. Then what does we see is that when Ex leads by Ey by 0 degree, or alternatively what we can say is that if there is no phase difference between Ex and Ey, then we will get a linearly polarized light, which is given by this line, straight line, which is very much obvious, we have already talked about it. Now, if Ex leads Ey by pi by 4, then we get an elliptically polarized light. If it leads by pi by 2, then you see the ellipse got rotated, the major axis of the ellipse earlier was in this direction, now it is vertical, and now we keep increasing the angle and you see that the ellipse again got rotated, and for pi phase difference we again get linearly polarized light and then again elliptically polarized light and again linearly polarized light. Now, we see that this is a full rotation of 2 pi, and after 2 pi rotation this linear representation repeated itself. Okay. After full circle the polarization repeats itself. Okay. Now, have a look here at this pi by 2 and 3 pi by 2, they look similar. The ellipse which is drawn for phase difference of pi by 2 and 3 by pi by 2, they are vertically oriented ellipse. The major axis of these two ellipses are vertically oriented, but the sense of rotation of the electric field tip is opposite. Here the rotation is in anti-clockwise direction, while it is in clockwise direction for 3 pi by 2 case. Okay. Similarly, you can see for the other figures also. Okay. Now, in the here the epsilon was positive. Okay. The same thing will be repeated if you take epsilon negative. Okay. Here all the angles are the top angles are measured in negative, there is a minus sign, and in this case Ey leads Ex. Okay. Now, if there is if the phase difference is 0, then we will get the same type of state of polarization which we got here. This case is similar to this case. For pi by 2 we get an ellipse, sorry, pi by 4 we get an ellipse, pi by 2 different orientation of ellipse, and so on and so forth. Okay. Now, from here till here we see a type of rotation which is different from these rotations. The 3 ellipses here in the first block have different sense of rotation than the 3 ellipses here on the right block. Okay. here the ellipses in block 1, the ellipses are rotating in anti-clockwise direction. Here in the right block, the ellipses are rotating in a clockwise, or tip of electric field vector is rotating in a clockwise fashion. Now, therefore, the second block where the tip of electric field vector is rotating in a clockwise fashion is called right handed, and therefore, this polarization is called right elliptically polarized light, while in block 1 the rotation is in anti-clockwise direction, it is called left elliptically polarized light. Okay, and this correspond to the definition of left and right circularly polarized light also. Yeah, the sense of rotation which we introduced or which we discussed in the last class is the same here. Here, just due to the change in the magnitudes of Ex and Ey component, the circle got converted into an ellipse. Yeah, and this is all for elliptically polarized light. Okay. Thank you for hearing me, and we will discuss or we will start interference from the next class. Thank you.